What I now want to talk about, and we're going to do a demo later this morning, is about stimulus presentation and synchronization. Oh, and I should get my remote. Just a second. So yesterday morning we looked at this part, so the green arrow. Yesterday afternoon we looked at this part, the purple arrow. But what is important is that the information about what the participant is doing and when the participant is doing it is also recorded together with the EEG data. So this morning we're going to look at this part. Let's first zoom out a little bit. So this is also what Mikkel covered in his lecture on Monday. So we have different types of studies. Studies like different types of research questions, different types of how we address the research question. We have observational studies, and we have experimental studies. Observational studies is if we look at something, if we record data without any intervention. So this is, for example, what we do if we record data from an epilepsy patient. The patient is simply sitting there and we don't tell the patient to do anything. It becomes experimental as soon as we start manipulating the experimental setup and the conditions by flashing a bright light. So if we use the photostimulator, then we're conducting an experiment. Or by asking the patient to hyperventilate. Most cognitive research is experimental. So in most cognitive research questions, we are using an experiment. That's what we looked at yesterday, is how do we design an experiment? How do we design a task? How do we present material on the screen, or how do we present sounds? And in cognitive experiments, we tell the participant what they should do. For example, look at the screen, look at the fixation cross, press a button, and we present stimuli and record responses to very specific conditions. So in these experimental situations, while we're recording EEG, we have to know when the experiment actually takes place. So let's go a little bit into experimental design and terminology. And here I'm repeating what Mikkel already explained on Monday. The brain is active and the brain is doing many things at the same time. So there's always this overlap of spontaneous brain activity, thinking about what we had for breakfast, at the same time listening to the presentation, looking at the screen. And the EEG signal is very noisy. So if we want to, we have to deal with that noise and we have to deal with the spontaneous brain activity. Also, the brains of different people are not exact copies. So there's also variability over participants. And cognitive processes can be implemented differently. So perhaps the way that you listen to language is different than how I listen to language. Because language for me is implemented in a different manner. I learned English at a different age, etc. So therefore, in general, what we need is we need many repeats of the experiment to make sense of the data. The signal of interest is very small, so if we repeat, we can average, and then we average over many trials. So those are repeats within the participants, and we average over many subjects. So a typical EEG study, we would have one participant come to the lab, we would have a few hundred trials. And then in total, we would have possibly 30 to 50 participants come to the lab. So we have the analysis within the subject and we have the analysis at the group level. For the experimental design that we use for each of the participants that we invite to the lab, we can either use an event-related design or a block design. In an event-related design, each trial is a different condition. So in each trial, something happens and the participant can usually not predict what's going to happen. So yesterday we looked at the oddball task, like with beeps and boops, like with different tones, and then the participant cannot predict which one is going to happen. which is exactly the purpose of how we want to study this, because we want to study the expectation of the sound, if the sound is expected or if the sound is unexpected. So the conditions are random over trials. We also have block designs. And in a block design, all the trials that we have within one condition are of the same condition. So block designs, they can work well, but block designs are not suited for all types of for research questions. For example, if there's surprise or attention, block designs might not be optimal. What we do then in a block design is that if we have two different conditions, that every block is a different condition, and typically we randomly shuffle the conditions over the blocks. So in the first block you would have condition A, in the second block you would have condition B. But then if the next participant comes, the next participant is going to have condition B first and then condition A. So randomly shuffling is always important. The reason for random shuffling being important is that we have confounds. If you always present stimulus A first and then stimulus B, or if you present block A first and then block B, then during block B, the participant has been sitting in the EEG lab longer, and perhaps the participant is fatigued, is bored, doesn't want to do the task anymore, and then systematically the cortical processing in task B would be different than the cortical processing in task A. So that is something that we might, in the block design, that we cannot avoid for a single participant, but by randomly shuffling the blocks over the participants, we can counterbalance. So one participant is fatigued in task B, the other participant is slightly more fatigued in task A. And then over participant, this effect of this confounding effect of fatigue in the experiment is going to cancel out, or it's going to be averaged out. Also yesterday I helped a few people with their PsychoPy codes, and we already looked at how to present random stimuli, like random words or random tones. So what we often do is we generate not totally random, but we generate pseudo-random sequences. So for example, if you present a totally random sequence of tones, standard, deviant, it can happen that the very first tone is going to be deviant. That's not really expected, but it can happen. It's going to happen in some of the participants. So what we often do is that we randomize, but then we use some rules. For example, the rule that the first tone that's going to be presented is going to be a standard, so that the participant gets used to the standard tones. Also, we might have a rule that the deviants are not going to follow each other, so that whenever there's a deviant, that the next one must be a standard. Otherwise, the participant might get too much used, or might get too much expectations of there being many deviants. So there's a number of things that we do in our experimental design. So we randomize trials in an event-related task. We randomize between blocks, and we counterbalance. And then in the randomization, we make sure that we have a nice randomization, not a totally random one. There's a number of terms that I've now been using. So we have the visit, the participant coming to the lab. Then we have a session. Usually if the participant comes to the lab, we do a single session. But if the participant is in the lab the whole day, we might want to do a session in the morning and in the afternoon. Sometimes we do an experiment in which we ask the participant to go home and sleep. Then we would have two sessions, one on the first day, one on the second day, and we would also have two visits. A block is what we call a part of an experiment, like a part of a session. So in an experimental session, we might have multiple pieces, and then we would have a break in between. And that's what we call the blocks. So a block is something that has a break, and then the next block starts. Sometimes within a block we have mini blocks. And then within the block, I should also say, prior to going to the mini blocks, we have runs. Runs are considered the moment when we start the amplifier until the moment that we end the amplifier. Very often, in our experience at the Donders, we do one run per session. So we just switch on the amplifier once the participant is set up, and we switch it off when we're ready. But this is a choice that other labs might make differently. So perhaps what you want to do is you want to have runs for each of the blocks. So if you have 3 blocks, that you're going to get 3 files on disk. Whereas the choice that we make is to have 3 blocks in one run, which means that we have 1 file on disk. And that's what you're going to see this afternoon in the pre-processing. So in the pre-processing, I'm going to show you how the experiment was designed, and you can recognize that there are 3 blocks in one run, in one file. Then sometimes within a block we have mini blocks, so we have a few trials that go together, and then we have the trials. The trial is really the repetition, is the core element of the experimental design. So in one trial, something happens that the participant has to pay attention to and has to do something with. Okay, so a trial is an important experimental concept, and then we have 2 things that we often use, and they're very related to each other. It's the inter-trial interval. So it's the time from the end of one trial to the beginning of the next trial. Or it's the interstimulus interval. And the interstimulus interval is often the time from the beginning of the trial to the beginning of the next trial. Mikkel already mentioned that in order to have the participant pay proper attention, but also to make sure that the participant, that physiological artifacts from the participant, such as the heartbeats, do not become synchronized with the experimental task, we often have a random inter-trial interval or a random interstimulus interval. So we're not presenting the trials at exactly the same distance in time, but we're presenting them with a little bit of jitter. And that means that the brain activity becomes less correlated over trials, and that helps in averaging out the noise. Of course, there are experiments where the timing is actually part of the research question. So perhaps you want to have an experiment in which the interstimulus interval is actually very nicely controlled. So if you're, for example, studying rhythm perception, well, of course, then you want to have them very precisely timed. And then perhaps the experimental manipulation could be to have a fixed interstimulus interval, and then occasionally one stimulus that is presented a little bit earlier or a little bit later. So that's how you should think about timing in the experiment. Here you see such an experimental design with time indicated as an arrow along the horizontal axis. And this is one trial. So yesterday with PsychoPy, we already made a fixation cross. And the fixation cross is something that we use a lot, because what we've seen yesterday as well during the experimental session, if you move your eyes, you get large artifacts. So we want to prevent our participants from moving their eyes once the trial is happening. So that means that we first have the participant do nothing, then we present the fixation cross, and then we present the stimulus. And then optionally, depending on whether this fits with the task, you would record a response. I'm just going to try the other microphone. So this is then one trial. So it starts with the fixation cross, the stimulus, and sometimes the response. And then we have the second trial. The trial interval is the time between this one and this one, because you could say the blank period, the participant is not doing anything, is not seeing anything. So here, the inter-trial interval is 2 seconds. Whereas the interstimulus interval goes from here to here. So this is the terminology that we often use. Okay, so this is when we look at it, at the experimental design in great detail. If we then zoom out, you can see that we have, in general, we would have an instruction. So we would tell the participant what to do, and very often we present on the screen what the participant has to do. So we explain the task to the participant prior to the experiment start, but then we show it on the screen once more, and then the participant presses a button to indicate that the experiment can start. Then we have trial 1, trial 2, up to trial n. Then we would take a pause and then we would again repeat the experiment. And the pause indicates the difference between the blocks. Any questions about this? So yesterday in PsychoPy, we mainly looked at, the other direction. We mainly looked at this level. So we looked at how can we present one stimulus, or how can we present two stimuli. What we did not yet get to is how can you go from one stimulus to two stimuli to a whole experimental design with many trials and with many blocks. So what we would do in PsychoPy, in the programming language Python, is that we would write for loops. For each of the trials, present the trial. And then around these for loops, we would write a for loop. For every block, present the trials in that block. So what we've been doing yesterday in PsychoPy is really at the smallest level, and then we add stuff around it to set up the experimental control. So for this we use stimulus presentation software, and stimulus presentation software has the characteristics that it can play sounds, it can show text, it can show images, it can also show videos, and it can record responses from the participants. It can use the keyboard, the mouse, the joystick, like a button box, and what is very important for the stimulus presentation software and what makes it different than what I'm doing now, because I'm now playing images and text from presentation, is that stimulus presentation software is very precise in when it does it. So yesterday you saw that we have to flip the screen, and exactly at the moment that the screen is flipped, we would want to send a trigger. Because the EEG acquisition for the EEG acquisition, we need to know when the stimuli exactly happen or when the response exactly happens. So the stimulus presentation software can write the exact timing of the stimulus to a log file, which is usually just a text file that is on the stimulus presentation computer. But specific for EEG, the stimulus presentation software can also send a trigger. And a trigger is a small signal that is sent over a cable towards the EEG device. And we're going to show you in the hands-on session or in the demo after this lecture on how that looks like. And usually the stimulus presentation software allows you to program an experiment in the form of a script. And that's what you've been doing yesterday. You've made a very first script in which you put together a few trials. So when you move from one trial to two trials to the whole experiment, you're basically making the script larger and larger. And that's why you can see that the stimulus presentation software also handles the instructions. It can handle training trials, because perhaps the participant first has to get used to the button box, to the keyboard, or to the task. It then has the experimental trials with the stimuli, and it records the responses, which again is very important, because it might be that you're asking for a response, and then responses might be correct or incorrect. Responses might be relevant because of the time that it takes for the participant to respond. Perhaps you want to compare the slow responses to the fast ones. And it provides feedback to the participant. So the feedback to the participant is also important, because you want the participant to pay attention. And if the participant is looking at the screen and not really pressing the buttons, what you want is the stimulus presentation software to say, hey, pay attention, go faster, you're not fast enough. So that is something that the stimulus presentation software does. So the stimulus presentation software often is used to do the analysis in real time of the behavior, and to use the behavioral analysis to provide feedback to the participant. Not only to speed the participant up, but also to tell the participant that they're doing good. So you, for example, say, oh, that was a correct response. This is an incorrect response. So those are the things that we do in stimulus presentation software. There are many different softwares. Some of them are open source and free, and some of them are commercial and paid. So yesterday we've been using PsychoPy. PsychoPy is for behavioral experiments in Python. And PsychoPy also has a sibling, which is PsychoJS. PsychoJS is implemented in JavaScript, and it is more designed to be used in a web browser for behavioral tasks that you run over the internet. So it's not something that we use a lot in the lab. Another Python-based toolbox for stimulus presentation is Open Sesame and Experiment. And then other toolboxes in JavaScript are JS, Psych, and LabJS. And if you're interested, you can look up the slides later and you can find them online. Then on the side of the commercial or the paid software, we have NBS Presentation. That's the software that we use a lot at the donors. There's ePrime, there's Gorilla. Gorilla is again more used for experiments that are online, that you have the participant do at home, so not so much for using in the lab. Then we also have software that is open source but not completely free. And the big example there is Psych Toolbox. So Psych Toolbox is a very widely used stimulus presentation software, and rather than using Python, it uses MATLAB. The nice thing is that a lot of the analysis software is written in MATLAB. So when students learn how to analyze the data, they learn how MATLAB works. And then if they can also do the stimulus presentation in MATLAB, that actually makes life easier. Of course, you could also say the other way around. So once you learn Python, you can do both stimulus presentation and the analysis in Python. What is an important characteristic of this software is that it has to be very precise in the timing. And that is where a lot of the components that it uses are borrowed from gaming engines. So gaming programming environments such as Unity or Unreal Engine can also be used to program experiments. It's just that they're not so handy, because they're in C++, so you really have to have low-level programming knowledge. And there's a lot of concepts that we use in our psychological experiments, behavioral experiments, that you would then have to implement all yourself. So that's why, in general, we would go with the open source or the commercial software for stimulus presentation. Experimental design is important because it relates to timing. So we want to know exactly what the subject is doing or what is the subject is seeing at the exact time. And we write everything to a stimulus presentation log file. And we send a trigger to the EEG system at the start of every block, which can indicate a condition. So we're not only writing that a stimulus appeared, but we're also writing which stimulus appeared. And that means that we can send we can send triggers at multiple moments in time. For example, we can send a trigger at the start of the trial. At the onset of the fixation cross, at the onset of the stimulus. So this is where the stimulus code will be used. Just a sec. We can also send a trigger at the moment of the response. And if we're doing a real-time analysis of whether the response is correct or incorrect, we can also send a trigger at the moment that we provide the feedback. So if the stimulus presentation software has already determined whether a response is correct or incorrect, then we don't have to do that afterwards in the analysis anymore. So if you look in the event file or in a trigger channel that comes with an EEG system, there's a whole sequence of trigger codes, coding the different elements that we have within a single trial. A trigger, so what I'm doing here is I'm recording the audio and I'm recording the video so they can have the lectures afterwards. And since the camera is in the back, it's not going to pick up my voice very well. So that's why I'm wearing a separate microphone. And in the editing of the video, what I have to do is I have to synchronize the audio and the video and the audio with each other. For that, like in old-fashioned movies, you might know that they use a clapperboard like this. So a trigger is basically the clap of a clapperboard. So the clap of the clapperboard records both visually and auditorily the moment that something happens. The clap itself is not really relevant, or the movement is not relevant, but you can see the movement in the image, in the video, and you can hear the clap in the audio. And then you can align them. So that is basically what we're doing when we synchronize our behavioral experiment with the EEG recording. We're sending a trigger, and the trigger is like the clapperboard. Any questions about this? All clear? Okay, so we're using a computer, and it is important to know some of the details of a computer, and especially of a computer screen. A computer screen, like as you know, has a specific resolution. So nowadays they often have a resolution of HD, which is 1900 by 1000 pixels. Screens also have a refresh rate. So a screen might have a refresh rate of, for example, 60 Hertz. That means that a new screen is drawn 60 times per second. That also means that drawing the screen takes some time. And if we have 60 Hertz refresh rate, then we have 60 frames per second, which means that one frame takes 16.6 milliseconds. I'm going to switch back to the other microphone, see whether that works better. Okay, can you replace the batteries? There should be batteries on the table. So a computer screen is not continuous. A computer screen has like discrete moments at which something happens, and also it has these pixels with the red, green, and blue, etc. So that is important for us to present because the brain is continuous. The brain is much faster than a computer screen. So if we're using a computer screen to show things, well then we have to know exactly where in time that happens. So this is something that we already saw in the practical session. So what we do is we make a stimulus. So we define the characteristics of a stimulus. Yesterday we made a text, and then we draw the stimulus. Drawing the stimulus happens in memory. It does not happen on the screen. Because if you would draw it on the screen, you would see things moving. That's not possible. So what we do is we draw the screen in memory, and the actual display of the screen is updated all at once. So what we can say is that we have one picture in memory, and that picture in memory then all of a sudden becomes the picture that we see. And that is what we call flipping. So we have one invisible screen in the background, and we have a visible screen in the foreground. We draw on the invisible screen, and then we flip it, and then it becomes visible. So this is important, because it's at the moment that the screen becomes flipped to visible, that is the moment that we want to send the trigger. So we're not sending the trigger at the moment that we're drawing, because the drawing happens in the background. We send the trigger at the moment that the screen is flipped. And that is something that we did not get to yesterday, but we're going to look at that today, is how we're going to synchronize the flipping of the screen with the sending of the trigger. If we send a trigger, we need to have a cable between the computer that is doing the stimulus presentation and the EEG system. And for that we often use a trigger cable. Actually, let me just get one. So this is like a rather experimental. I'm just going to switch over again. Man, I'm just so fed up with this. So this is a trigger box. Actually, it's not a box because you can directly see the components. This cable goes into the EEG amplifier. This trigger box has a USB connection, and the USB connection goes to the computer. So that's what we use this cable for. What is important is that there's different EEG systems, and these EEG systems, they all have their own trigger ports. So we're going to look in, so we have the 64-channel Saga system from TMSI. It has a different trigger port than the 32-channel GTEC Nautilus system that we had in the middle. So if you have to make a trigger port, you always have to look at how the port is organized. So the EEG system amplifies the voltage differences and digitizes them at a fixed rate. And this parallel input port, that's what we use for triggers. And each pin of this connector represents 1 bit. So in digital computing we have, in digital processing we have bits and bytes. And by using a sequence of bits we can form a byte. And each of the pins corresponds to a bit. And then the pins accept TTL, transistor logic, voltage levels, which we can put low or high. So either the voltage is at 0 volts or the voltage is at 5 volts. What is important is that some of the EEG amplifiers will work with 5 volts, some of them will work with 3 volts or 3.3. So that is always something that if you make such a cable, you have to look this up in the specification of the amplifier. Then this is the specification for the GTEC Nautilus amplifier, the one that we had in the middle. And it specifies here which pins can be used and which voltage can be used on those pins. So what I did is I made a cable for this. And on this cable I can then send individual bits. Bits can be combined. Because if I send, for example, a fixation cross, I can use the first bit. The first bit means in decimal terms means the number 1. If I send a stimulus A, I can send the second bit, which in decimal means the number 2. Stimulus B, I could use the third bit. So that would be in decimal terms, would be the number 4. Because the way that these bits work is, it's 1, 2, 4, 8, 16, 32, 64, 128. If we have a left-hand response, we can also code that in a bit. If we have a right-hand response, we can also code that in a bit. But what if the participant presses 2 buttons at the same time? Well, then we would get 2 bits that are active, and then we would get this bit and this bit. And the decimal representation of this is the sum of the 2. So the decimal representation is 8 plus 16 is 24. So these are the numbers that you're going to find in your EEG acquisition file. And if you see a 24, then it has to occur to you, oh, the participant pressed both buttons at the same time. It's perhaps not what you expect because you told the participant to press either left or right. Well, yeah, participants just do random stuff. So it is important to understand the nature of how these bits, how they relate to the trigger codes that you send from your stimulus presentation software, and how they relate to the events or the markers or the trigger markers that you find in your EEG file. So just a little bit more background on the decimal numbering. So with binary numbers we use 2 digits. So we use 2 symbols, the 0 and the 1. And these are called bits. And as with decimal numbers, we interpret them from right to left. The rightmost bit represents 0 or 1 times 2 to the power 0. The second bit from the right represents 0 or 1 times 2 to the power of 1. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So that's 0 times 2 to the power 0 is 0, etc., etc. So 1 times 2 to the power 2 to the power 7 is 128. And then we take the sum of all these numbers. And in this case, this binary pattern represents the decimal number 202. So this is something that you will often see. And since we can code a lot of different details in the triggers, it is important to think about how you're going to use these bits and how you're going to use these numbers. What we often do is that, for example, that we say, well, I don't care about individual bits, but all the stimuli from 0 to 100, sorry, all the triggers from 0 to 100 are stimuli, and all the triggers from 100 to 200 are responses. Because then it's just easy to remember, okay, so the ones below 100 are stimuli, the ones above 100 are responses. So you don't have to think about the bits, but you have to be aware of that the communication happens with bits. Some EEG systems actually also support that you only have a single bit, and that's what we're going to look at with the jitter system. So we can either tell the software to interpret each bit by itself or to interpret the bits together. If you interpret each bit by itself, then with 8 bits, you can only send 8 different triggers. Whereas if you interpret the bits together, with 8 bits, you can represent 255 triggers. And of course, with 255 triggers, you can encode much more detail in your trigger channel. In the old days, when I started doing EEG experiments, serial ports were used for the mouse, for modems, etc., and parallel ports were used for printers. So this is a parallel port, this is a serial port. But nowadays, our computers don't have parallel ports anymore, because we're not connecting to printers using parallel cables, we're connecting everything with USB cables. So USB ports are serial in nature, but the EEG systems, they still have parallel ports. So you just see some port types. And that is why we're using these boxes, as already shown, to translate from the serial communication of the computer to the parallel communication that the EEG system expects. So we have many different types of these. Actually, we also have this one. We brought it, but we're not using it. This is the one that I just showed. Yeah, Mikkel, could you get the other one as well? I can just show it. So this is the one that I just showed, but it's just like in a different, or actually it's not in any enclosure, but it has these buttons. You can put your fingers on it and you can press the buttons with your fingers. So the buttons are just aligned. So that is this one. So this is an old box that we used at the Donders. I just was able to take it with me. So this is another box. This is actually, it's a version of this one. On one side it has a USB connector, and on the other side it has a cable, and this cable goes to the computer. This is the cable that we got for the TMSI Saga system. Regretfully, it has the wrong adapter. So I'm a little bit annoyed because I asked the company to provide me with a trigger cable and they gave me the wrong cable. So we cannot demonstrate how the triggering works with the TMSI 64-channel system, simply because we don't have the right connector on this side. But we can show it with the GTEC Nautilus. So different companies have different ways of triggering. This is the trigger box that comes with the Brain product system. This is a trigger box that you can buy separately, and this is I think a relatively fancy one. It also has audio triggers. So you can directly connect a microphone, which means that the trigger is going to be sent when the subject starts speaking. So that's convenient, because then you don't have to record the audio, because you just record the onset of the audio. This is a simple one that I showed, and these are very similar ones. So a lot of labs make these trigger boxes themselves. Actually, I would say this is like a nice engineering project for engineering students, if you have them on a university, to help with synchronizing the computer with your EEG equipment. You can also buy them. A lot of labs buy them. I think a box like this is a few €100. A box like this, just the electronics, is €10. So that's your choice. So if you buy them, if you build them yourself, they can be really cheap. If you buy them, they can become really expensive. And for an electronics engineering student, this is not really very complex, but it's just like a fun project. It is important, like if you want to buy a box, to think about what the characteristics are. So some converters only do outputs from the computer to the EEG system. Some converters do both input and output. So the one that I have not only sends triggers to the EEG system, but also records button presses. Some converters only have 8 bits, like a parallel port, and some have 16 bits or even more. And the more bits you have, the more information you can encode. And some converters, as I already said, they have additional inputs, for example, for audio, so that you can detect the onset of a sound when the participant is, for example, speaking, or for a photodiode. And we're going to demonstrate a photodiode as well. A photodiode is let me just show it. I've attached the photodiode here. So a photodiode is basically a light-sensitive detector. And what we do is we place it in the corner of the screen. If we then present a stimulus, then we can have a small white square in the corner of the screen that flashes exactly at the moment of the stimulus. So we know exactly when the stimulus appeared by measuring it. So rather relying on the computer sending the trigger, we detect the trigger from the screen. And that is very important, especially if you have a new setup and if you don't really know how well the timing of the system is. So this is something that we often use if we replace our computers. So if we replace our computers, we're first going to test all of our computers whether they still have correct timing. And once we've determined that the timing is correct, then we don't use it anymore. But if you're not sure, a photodiode can actually help you to determine the timing. Okay, so I've been telling about these, that we have these bits, and a bit is basically a voltage that goes up, but everything that goes up must go down as well. So some converters allow you to specify how long the pulse should be on, so that it goes on and that it goes off. The one that I brought, I programmed it such that the pulse is long enough that you can see the LED flashing. The disadvantage of having a very long pulse is that the chances of the participant pressing 2 buttons at the same time and the 2 triggers interfering with each other also increases. And some of the converters allow you to specify whether patterns should stick or not. So this is the do-it-myself thing that I brought. So this is an Arduino. An Arduino is an open source electronics project platform. So these boards, they're really cheap. They're only a few euro. They have a small microcontroller of them. And the Arduino Uno is the simplest version of this. It has a USB input, it has a microcontroller. It has 16 bits input and output, and you can program it either with C or with Python. And many EEG labs use a board like this to build their own USB to parallel port converters. So that's what I've done, and also this code is open source, so you can use it in your lab as well. So you can have a look at the box that I brought, and you can copy this. What I already mentioned, what is important is that it has to be adapted to the specific EEG system that you have. So you have to look into the documentation of your EEG system, what type of connector to use, which pins on the connector to use. So in this case, I had to use pins 1 to pin 8, and what voltage to use. So in this case, all the pins can take 3.3 volts. Some of the pins can also take 5 volts. So what I did is I gave all the pins 3.3 volts. And then of course there's a ground, because there's a voltage difference. Okay, so not all EEG systems, like nearly all EEG systems that are used for research have a parallel input port, but not all EEG systems have one. For example, the unicorns, the very small EEG systems that we had there, they're wireless. There's no parallel input on those. Also, clinical EEG systems, they might not have a parallel input port to sending triggers. So what do you do then? A very common and widely used technique is to use lab streaming layer. Lab streaming layer is an open source library that is available for MATLAB and for Python, and it can send timestamped data over the network. So with lab streaming layer, you can set up your lab with multiple devices, and all of the devices are sending the data over the network to one computer where it is being recorded. What I commonly use, if we use this, is Lab Recorder. Lab Recorder records all the incoming data. And the interesting thing is that all the packets are being timestamped at the moment that they're being transmitted. So that means that on the receiving side, you know exactly when on the computer the packet was created, not when it was received, because the network is going to have delays. So that also means that if you use lab streaming layer to send the markers, you also need to use lab streaming layer to record the EEG, because they need to be sent with the same timestamps relative to the same network clock. So lab streaming layer supports a lot of amplifiers, but if your amplifier is not one of them, then you might be able to use an analog input. And some amplifiers have an analog input, and if you just use some resistors to make the voltage smaller, you can put an analog input into the amplifier. If that still also doesn't work, a lot of amplifiers have the ability to record in the software when something happens. And especially in clinical amplifiers or in clinical recording systems, you can make an annotation. So with such an annotation, you can specify when the stimulus happens. Of course, if you have to press a button as the experimenter, you're not going to be very precise. So you're going to be at most like 500 milliseconds precise or so. So I would say this works at the start, at the end of the experiment. This works, for example, if you tell the subject, now close your eyes, and then you press the button. This doesn't work if you're presenting stimuli on screen where precise timing is needed. So this doesn't work for event-related potentials. But it does work for longer resting state recordings. Oh yeah, lab streaming layer. I think I'm gonna skip this slide. It's a little bit too technical for now. The slide is in the slide deck, so if you want to look it up, you can look it up later. Another thing that we have to think about if we're sending very precise timed things is that we have delay and jitter. And delay and jitter can be compared to accuracy and precision. So if I'm trying to hit a target, of course, this is what I'm aiming for. But if there's a systematic difference, this is what I might get. And if I'm a sloppy shooter, this is what I might get, or this is what I might get. So what you see is that there's two different types of error. One is a systematic error, and the other one is a random error. The delay, that is a systematic time difference, whereas the jitter is the random time difference. If you do an EEG experiment, and if you're using speakers, for example, one of the systematic delays that you're going to get is that sound travels with 300 meters per second. So that means that if the speaker is 1 meter away, the sound is going to take 3 milliseconds to reach the participant. If the speaker is 2 meters away, it's going to take 6 milliseconds to reach the participant. So these are things that you should just be aware of. And 3 milliseconds is not something that we usually worry about, but it's just important that you know about this. So delay is something that we would typically try to measure for a lab setup. But what is more important is that you try to reduce the jitter. Delay means that the ERP component is going to shift in time, but the ERP component is still going to be there. So you might expect an N1 component at 100 milliseconds, and then you're finding the N1 component at 120 milliseconds. Okay, so that still works. What is more problematic is that there is jitter, and with jitter, what happens is that each trial is randomly shifted. It's like taking a photo while you're moving the camera. So what happens is everything gets blurry, and the peak amplitudes are going to get much smaller. And if the jitter is large enough, you're not going to see anything. And since with event-related potentials, we have very short peaks that we're interested in. So often the peak is so for example, here you see, like this peak is around 100 milliseconds wide. This peak is around like 50 milliseconds wide. If you're going to have 20 milliseconds of jitter, it's already almost going to be disappeared. So typically I would say a jitter of 5 milliseconds is acceptable. But more than that, and you're really gonna miss ERP components. And you're gonna lose your statistical sensitivity as well. So this is why you put so much effort into getting very precise timing, because if we don't have precise timing, we're not gonna see what the brain is doing, because the brain is much faster than the computer that we're using. That's what I had to tell about stimulus presentation and synchronization. Any questions?